עומר, תוכל להתחיל את ההקלטה?
התחלתי.
Okay, so welcome everybody to the final JIPS meeting of the spring semester. And today we're very happy to have Matan Shalev from Tel Aviv University to tell us about the scaling limit of high-dimensional uniform spanning trees.
Yes, thank you, Ron. And indeed, the title of my talk will be Scaling Limit of High-Dimensional Uniform Spanning Trees. It's based on joint work with Elinor Archer and Asaf Nachmias. And I'll start my talk by describing what a uniform spanning tree is. So we start with some finite and connected graph G. And a spanning tree of G is a subtree of G, a subgraph of G, touching all of its vertices, and it's a tree. It has no cycles. And when the graph G is finite, then obviously the set of spanning trees is also finite. So we can simply define the UST of G to be the uniform measure over all spanning trees of G. So that if G is the graph that we see on the left-hand side, then the UST of G is simply the uniform measure over this set of its 8 spanning trees. And today we'll be discussing scaling limits of finite USTs, meaning we'll take a sequence of graphs, of finite graphs, Gn, with a number of vertices tending to infinity. We'll scale the distances somehow after taking the UST of such graphs, and we will hope to find a limiting object eventually. And we'll do so in the mean field regime. Now, what does that mean? So, as in many models in probability, this one exhibits the following phenomena as well. So there is a notion of upper critical dimension, D, such that if we're working on a graph with a dimension larger than this D, the model kind of does what it wants. The geometry becomes trivial, and the model on these graphs behave as if we were in a geometrically trivial graph, such as the complete graph. So we will show what happens when the dimension is very larger than the critical dimension, and we expect the behavior to be more or less trivial, which means it will behave as if we were in the complete graph, which will be the first example I'll be talking about. So the complete graph will be denoted Kn, and the UST of Kn is just an n-vertex random labeled tree. And we can ask the following questions of global flavor. For example, if we pick two vertices in the UST, what's going to be the distribution of the distance between them? What is the typical order of the distance between them? The diameter, which is the maximal distance obtained by a pair of two vertices, how is this guy distributed? And is it of the same order as the distances, or do we expect something larger? And then the third question that can answer the first two is there a scaling limit to the UST of Kn? If so, what is the correct scaling factor? And also, in what sense do we take this limit? We have to speak of some topology for this limit to make sense somehow. And you can see the not very interesting sample of K20 in this slide. So it is known that if you take two distinct vertices of Kn, you take their UST, and you look at the distance, so the limit in distribution behaves the following way. You have to scale it by square root of n. So this is going to be the typical order of the distances. But actually, in the UST of the complete graph, much more is known. So Aldos in 1990, he showed that if you take this sequence of USTs of Kn, you view them as random metric spaces equipped with a measure, random metric measure spaces, and you scale the distances by square root n, then this sequence of random spaces, they converge in distribution with respect to the Gromov-Hausdorff-Prokhorov metric, GHP, which is a metric between metric measure spaces, to an object called the CRT, or the Brownian CRT, or Aldous' Brownian CRT. These are all the same object, and this is an object which appears as the scaling limit of many random trees. for example, Galton-Watson trees conditioned to survive, will also scale to this guy. So I don't want to speak about the CRT too much, but I do want to show one way to sample this CRT and to show that it has some nice relation to Brownian motion. So this is one way of sampling the CRT. In it, we start with a Brownian excursion, which is simply a Brownian motion condition to return the values 0 and times 0 and 1. And we define, after taking this Brownian excursion, we define the following pseudometric on the interval 0, 1. So we think of S and T as 2 times, and the distance between S and T will simply be twice the sum of the values returned in these times minus twice the minimum of the excursion in the interval between S and T. So this is a simulation from Wikipedia. Maybe I'll switch to an easier excursion. So suppose that the left-hand side excursion is our Brownian excursion. So we can see that this is indeed not a metric because, for example, there are 2 points marked in 1. So the value the excursion returns on both of them is the same, and the minimum in the interval between them is indeed returned in the boundary. So the distance will be 0. So in order to make this pseudometric into a metric space, we have to take the quotient. So our new metric, random metric space, will be the 0, 1 interval modulo this equivalence relation. And this random metric space is the CRT. It has a distribution of the CRT. After doing it, we get a tree. So you can see we identify this whole part with this part, which becomes this part on the right-hand side. So every such an excursion defines a tree. And this is our nice object. Hang on, okay. And what's nice about this relation is that now we can calculate some properties of this limiting object, the CRT, in terms of Brownian excursion. So for example, if we want to talk about the diameter of the CRT, then this is going to be its distribution, right? We simply go over all pairs of vertices, of times, S and T. And this is just, we take the supremum, and this is the distance we defined in the previous slide. So, for example, it makes sense that this nice random variable, so we can do some Brownian motion magic, maybe, and using Brownian motion tools, we can calculate its density, which is this unpleasant sum given in 2. But the real reason I'm showing this random variable in this weird sum is because what happened is the other way around. So what really happened is Sekeresh in 1983, he investigated the UST of Kn, the n vertex random label tree, and he wanted to know if there is a limiting distribution to the scale diameter. So, and he indeed found out that if you scale the diameter by square root n, so you have a limiting distribution with a density given by this ft. Then in 1990, Aldous showed that these USTs that Sekeresh investigated, they converge after a proper scaling to the CRT. So, and the CRT can be sampled using a Brownian excursion. So we get immediately that the density of 1 is given by 2. And actually until, I don't know how many people tried to actually calculate the density of this one directly, but up until 2015, this was the only way to calculate its density. You had to go, in order to calculate this random variable, which depends only on Brownian excursion, you had to go through the theory of random trees and Sekeresh's result and Aldous's result, and to find out that the density of 1 is 2. In 2015, Wang managed to give a direct proof without going through trees that this is indeed the density that we see here. This is an image, a figure that you have to see in every talk, that that reminds the CRT. So it's due to Igor Gorchemsky, and this is a sample, I guess, of the complete graph with many vertices properly scaled. So this is how the CRT looks like. This is maybe okay. So we continue with our result, and this is our result in maybe its most interesting case. As I mentioned at the beginning of the talk, we want to talk about the UST when the underlying graph is of high dimension which is larger than the critical dimension. And the most natural graph to consider then, if we look at finite graphs, is the d-dimensional torus. So we look at the d-dimensional torus when d is larger than 4, strictly larger than 4. The side length is going to be n to the 1 over d, so the total number of vertices will be n. And we simply take the UST of this sequence of tori with the number of vertices going to infinity. And what we get is the same behavior as in the complete graph. So if we scale these guys properly, meaning by some constant times square root n, so we get that as random metric measure spaces, they converge to the same CRT with respect to the same GHP topology. Maybe two things I'll mention here. One is that this beta D is the only place maybe that we see here some of the local structure of the torus. But this beta D, as we take D to infinity, we become more and more similar to the complete graph, and this beta D tends to 1. In lower dimensions, we do not expect the CRT to be the scaling limit, except in D equals 4, where we still expect to see the CRT as the scaling limit, but we also expect to have some logarithmic correction. So it will not be scaled by square root n exactly. This is the critical case. It will be scaled by square root n times some logarithmic correction. In lower dimensions, the distances will be much larger than square root n between two vertices, and we do not expect to see this behavior. So this is maybe the most special case of our result, which actually holds under the following assumptions. So before stating them, I'll just say I don't want to spend time talking about the ways to sample the UST, but this is a model which is really closely related to random walks and to loop erased random walks. So also to intersections of random walks. And this is mainly due to the fact that that usually when you want to talk about the UST, you use one of the two famous algorithms to generate it. So you either use Wilson's algorithm, which relies heavily on random walks and loop erased random walks, or Aldo's Broder algorithm, which also uses random walks. So therefore, the three assumptions that we have, so one of them is transitivity, but the other two are stated in terms of the random walk on the graphs. So the second one is mixing. We want the graphs to be mixing. So we want them to mix quicker than square root n, much quicker. This kind of means that if we take the random walk, we want to forget where we started the random walk on the graph before we make the typical distance steps. So we expect that in these graphs, the typical distance will be square root n. So we want to mix before we reach this typical distance. And the other property is escaping. So what we want to happen is that if we take two independent simple random walks starting from the same vertex, and we let them both run until mixing time, so we look at how many times their traces intersect, and we want the expectations of the number of intersections to be bounded by some theta. So this is somehow that we try to capture the notion of having a dimension larger than 4. This ugly thing is D. So I'll write it again. And indeed, when D is exactly 4, the mixing time is exactly square root n, and the expected number of intersections is logarithmic, but whenever d is larger than 4, we get that mixing and escaping, so this is in the torus. So whenever d is exactly 4, and we're talking about the torus, so the mixing time is square root n, and the number of intersections is roughly log n. But when d is larger than 4, then we indeed get that we have this alpha, and that the expected number of intersections is bounded. And then we get the same result. So let Gn be a sequence of such graphs, transitive, mixing, and escaping. Then we can find the sequence beta n of constants, sequence of constants, which is bounded from below and from above, such that under correct scaling, beta n times square root n, we have this convergence to the CRT. Again, with respect to the same topology, and this is the best we can achieve, because so there are some cases. For example, if we alternate between the 10-dimensional torus and the 20-dimensional torus, then we understand that we cannot have just one single beta, because to each of them there is a different beta d from the previous result. So we can alternate between graphs. So we cannot necessarily we cannot guarantee that there exists only one single beta. We have to take this sequence, which might alternate a bit. But we indeed get the same convergence. And I will also mention that about this escaping property, that if we look at the infinite case, when d equals 5, this is the first time that if you take two simple random walks starting from the origin, they will intersect one another only finitely many times.
Sorry, what is dynamics? What is dynamics on graphs?
Sorry, there's no dynamics on the graph.
But what is time? Mixing time.
Yeah, so the mixing time, so I don't want to really define it rigorously, but the mixing time, so you take a random walk, you start from some vertex, and you ask after how long. So this is just a simple random walk, or a lazy random walk. You ask how long does it take for the walk to forget where it came from, meaning how many steps do we need to take until the distribution is very close to the stationary distribution.
Thank you.
Okay, sure.
Okay.
Matan, aren't the limits on the bounds on the degree in the theorem? I wouldn't expect that without some information on the degree, you really have the limit infinite of beta n is positive.
So you're asking if there is a bound which is uniform over all n, because the graphs are finite.
Yes, exactly. If you're assuming here that the degrees are globally bounded for all your graphs.
No, I don't assume that. We still have what we want. The uniform bound we want to have is theta and alpha, but we don't require a uniform bound on the degree.
Okay, thanks.
Matan, I'm missing something simple. The tori has side length n to the 1/4 in the previous slide. So
1 over d.
1 over d.
Yeah, it's 1/4 in d equals 4.
This is what it is. Okay, yeah, thank you.
Yes. Okay. So this is our main result. And I've mentioned the GHP topology quite a lot until now. So let me talk about it just a little bit. So this is a way that we measure distances between metric measure spaces. We will work on compact metric measure spaces. And we would like to, I would like to explain to you when our two metric measure spaces are closed. So we start with E d mu and E prime d prime mu prime. And we want to know, for them to be closed, we look for two good isometric embeddings, phi and phi prime. We want to embed both of them into some common metric space. And we hope that their images in this common metric space will be close to one another in the following senses. So the first sense is the Hausdorff distance. So this one just wants the images to be properly aligned. We want them to look similar on this common metric space, and it does not look at the measure at all. The next thing we want to have is that the Prokhorov distance between the push forward measures that we get from these embeddings is close. And what we hope to achieve is that there is a way to couple the two measures after we do this embedding, such that with large probability, a sample according to this coupling will give us 2 points which are close to one another. So another way to think about this Prokhorov distance is that we want that after this embedding, if we pick randomly and independently k points from each of the measures, and we look at the distribution of the distances between them, then these distributions have to be close to one another. So this Prokhorov distance looks at the metric, but also at the measure, of course, because we want the measures to be close. And then we have eventually the GHP distance is going to be, we take an infimum over all embeddings, and for every embedding, we take just the maximum between the Hausdorff distance and the Prokhorov distance. So H stands for Hausdorff, P stands for Prokhorov, and the G is Gromov. And I think of the G as we want to embed the two metric spaces into a common metric space. So we can also have the DGP, which is without the H, which is we look for good isometries, but we don't consider the Hausdorff distance, but only the Prokhorov distance. So I'll continue with a basic example. So if X is just a 0-1 interval with the Lebesgue measure on it, and Y is a discrete approximation of it, it's just a graph on n vertices. The distances are 1 over n between two adjacent vertices, and we have the uniform measure. So an embedding we can take, it's not the optimal one, is to just maybe take embed Y in X in the natural way. The Hausdorff distance is going to be 1 over n, and the Prokhorov distance is maybe slightly more difficult to calculate, but we indeed can couple the two measures such that typically we see points close to one another. So these two guys are indeed close in the GHP sense. But if we do this annoying thing, we add a purple line of length 1 and measure 0, then these two guys will no longer be close to one another in the GHP sense, and this is due to the Hausdorff distance, right? Because if we because we added something of measure 0, so the measure on X prime looks like the measure on X without this purple line. So the Prokhorov distance, after we take a nice embedding of the discrete approximation into X prime, will still be the Prokhorov distance will be small. They will be close to one another, but you cannot avoid things of measure 0, because the Hausdorff distance sees it all, and these two guys will indeed have distance 1 between them. So this is indeed something that we will return to in a minute. So what are the consequences of the GHP convergence that we have? So in our settings, we know that the rescaled diameters converge. So we take the sequence of USTs, we scale it with this beta square root n, and these random variables converge in distribution to the diameter of the CRT, which we gave its distribution earlier in this talk. The rescaled heights converge. So if you pick a vertex randomly in Tn and you look at the distance to the vertex farthest away from it, then this thing, as we scale it again using the same beta and square root n, converges to the height of the CRT, where we do the same, and this height of the CRT has a nicer distribution. It's just twice the supremum of such an excursion. And we also have that rescaled simple random walks on the USTs converge to Brownian motion on the CRT. So this was a recap short recap of our result, and we'll begin now to talk about some ideas from the proof. So this was our starting point. So this is a nice theorem by Yuval Perez and David Revel, And they said the following. Fix some number k, and look at the sequence. Take again the d-dimensional torus when d is strictly larger than 4. It's not written here. And pick k vertices independently and uniformly from this torus, and you immediately get a random variable which contains the k choose 2 distances between them in the UST. And what they said is that if you take this sequence of random variables, you let n go to infinity, and you always look at the distribution of the distances between k points chosen uniformly from the torus, then this sequence converges to a random variable, which is obtained from the CRT in just the same manner. So pick k points from the CRT. So the CRT is a metric measure space. It has a canonical measure. You pick k points from the CRT. You look at the distribution of the distances between them. This is indeed the limiting object, the limit random variable of this sequence that we discussed, which indeed suggests that the CRT must be the scaling limit of the UST of the torus, but it doesn't really capture all of its geometric properties. And to help understand that, we return to this annoying X prime, which has the zero measure line attached to it. So if you look at x and x prime and you sample k points independently from each one of them according to the measures they have, you get that they have the same distribution of distances, right? The measure on x prime does not see the purple line. And so this suggests that we can build this annoying example in our case. So we can take the complete graph, Kn. We attach to the complete graph a path of length n to the 3/4. And if we look at the sequence of USTs on these graphs, we will get that distances converge, right? We pick k points along the sequence, but since the length of the path is just n to the 3/4, which is negligible compared to the size of the whole set, we typically don't see this path. So we still have this finite dimensional convergence, this convergence of distributions, which is also called Gromov-Weak convergence. But we surely don't have a convergence of the diameter, of the scale diameter, right? Because the diameter has to be larger than n to the 3/4. So this Gromov-Weak convergence is indeed very useful, but not useful enough to imply that we have a convergence of the rescale diameter. And so in order to strengthen this one, at first what we try to do is to show that the diameter is at least, we at least wanted to know that the diameter is indeed of order square root n. So this is a result with Peleg, Michaeli, and Asaf Nachmias from 2 years ago. And again, Gn is a sequence of graphs, which is transitive, it's mixing and escaping. Then we have this tightness result. We know that for every epsilon, there exists some a, such that the diameter of the UST is between a to the -1 square root n and a square root n with this probability. But this obviously also does not imply that there is a convergence of the rescale diameters, right? Because if we take Kn and now we attach a path of length 200 square root n, so the diameter will still be of order square root n, right? This condition holds. Distances will still converge to the distances in the CRT, right? When you pick k points, you typically do not see this path, again, because its size is small. But this path of length 200 square root n, which will appear in every spanning tree of this graph, will indeed affect the distribution of the diameter somehow, and we cannot expect, therefore, convergence of the rescaled diameter to the diameter of the CRT. So we needed a wiser approach, and for that we used we use the lower mass bound and the theorem of Freya, Ler, and Winter from 2015. And before I will read this theorem, I will just say that it is stated now for deterministic metric measure spaces, where the USTs that we have are random metric measure spaces. So this is the deterministic version, and I'll talk about the distributional version afterwards. So we start with a sequence of compact metric measure spaces that converge Gromov weakly, meaning that the distances converge to the distances in some limiting space, and which is of full support. And we want to strengthen this one. So the condition, the second condition says the following: let's define m and delta. For every n and for every delta, this will be the lower mass. And this lower mass is simply the infemal mass assigned by the measure to a delta radius ball centered at some element of the metric space. So we simply go over all elements in the metric space. We look at the delta balls. We look at the measure that is assigned to them, and we take the infimum of this one. And we want the infimum to be strictly larger than 0. But not only that, we also want that the infimum over n of this m and delta to be strictly larger than 0. And the reason for that is if this does not happen, then we can find a sequence of delta radius balls along the sequence of metric spaces with mass tending to 0. So we're afraid that maybe there is something which will not be observed by the measure in the limit because of that, because the measure on them vanishes in the limit, but you still see something which is of delta radius, meaning the metric is there, but the measure will not be there in the limit. But anyway, if this does not happen, meaning if condition 2 indeed holds, so we have this strengthening from Gromov-Weak to Gromov-Hausdorff-Blochow topology. We need the random version of it. So we take random compact MM spaces. We suppose again that we have this distributional Gromov-Weak convergence. And what we want now to have is that for every delta, the sequence Mn delta minus 1 is tight. So what does that mean? It means that for every delta and for every alpha, there exists some epsilon, such that for all n, the probability to see a ball in the UST such that if we look at its delta square root n radius, so the measure we have here is the uniform measure. So the probability that it sees less than epsilon n points is smaller than alpha. So we want to guarantee that with probability large as we wish, all vertices in the graph see at least a nice portion of it.
Sorry, what is Gromov-Weak convergence?
So the Gromov-Weak convergence is simply the Perez-Revel convergence that I showed before. We want that if we sample k points from the metric spaces x and d and mu n, then the distribution of the distance between them will converge to the distribution of the distances in this in x d mu.
Thank you.
Sure.
There exists x in the probability, right? This is not for.
Hey, Asaf, your voice is very weak.
Yes.
Could you?
Yeah. Okay. Yeah. Okay. Sorry. This is very important. Thank you, Asaf. Yeah. So the probability that there exists x, right? We want the whole. This is indeed a global thing that we want to show, right? We take in M and delta, we take the infimum over all guys in the metric space, right? So I just had to change this x to there exists x. Thank you, Asaf. And therefore, in our UST settings, what we have is this Gromov-Weak convergence due to Perez and Revel. So if we show this tightness condition of M and delta, we immediately get GHP convergence, which is what we want. So this is our aim now. This is an equivalent way of stating this M and delta -1 tightness. And the reason we write it this way is because typically we have that, the ball of radius r around some vertex x is roughly r squared. So we know that, so it's sometimes more convenient to write it this way, because if we look at the balls of radius c squared square root n, typically we see c squared n vertices, and this epsilon is kind of how much we deviate from what we expect to see. So this is our aim, and it's not such an easy aim, and the reason is that it's a global bound, right? You want to show something simultaneously for all x's, and we're taking a spanning tree here. So if we find out that one of the vertices have a large ball in the UST, then maybe it suggests that if you take a vertex far away from it, this one has a small ball, which is bad for us. So this is not so easy, and our strategy would be the following. We would like to prove a local tail bound, which will be strong enough so we can do some scale analysis or a bootstrapping argument to improve this local tail bound to a global tail bound. So our input, so I'm lying here just a bit, it holds for every r which is and epsilon small enough. But what we have here is that a nice bound about the probability that the size of the ball around a fixed x is smaller than 16 epsilon times what we expect to see. And just know that what we have here is stronger than any polynomial, and it depends only on epsilon. So this is our input. And then we do the following. We say, okay, if there is some vertex in the metric space in the tree that sees less than 16 epsilon r squared vertices, then what we do is we go on to the next scale. We look at the smaller radius, the radius r/2, and we ask whether the ball of the same vertex of radius r/2 is small or large. If it's smaller than epsilon r squared, then now we got that this ball, the number of vertices it sees, deviates from what we expect to see. It's smaller than 4 epsilon, the radius squared. So this is, here we get a better bound. But if the smaller ball is big, so this is also good for us. This is even better for us, because then it tells us, okay, in this r/2 ball around x, there are many vertices whose r/2 ball is small, and this is because their r/2 ball is contained in the r ball of x, which we know is small. Therefore, what we can do is we can start with this first event, and we decompose this one into 2 events, right? Either the smaller ball is small or it's big. The event that the small ball is big can be immediately dealt with using a Markov inequality, and this one it becomes slightly better. We get a slightly better bound. So what we do is we continue decomposing this one over and over again until we eventually get something which is strong enough so we can multiply it by n and get that it's very small, and we fulfill this dream that we had. So yeah, this is just going over the same argument again. So we understand that we want a global bound, but for this global bound, it is sufficient to prove a strong enough local bound. So I'll use the 10 minutes left I have to talk about how we get this local bound roughly. Now we fix some x. We don't need something that holds for all x. We fix some x, and we want to show that the probability that the ball around x is small is very small. So what we do is we fix some x, and we sample in some reasonable way some path emanating from x denoted by gamma, and we think of this gamma, we think of this one as the r prefix of gamma, or maybe r/2 prefix of gamma. And now once we have this path, we want to start sampling trees on this path. There are trees hanging on vertices of this path, and we want to say, okay, if we sample the whole trees in the UST hanging on this path, we eventually will get at least the epsilon r squared vertices. So at the first step, we look at these epsilon to the 1/3 r trees. And we know that in expectation, the number of vertices they will have in the first r/2 levels will be much larger than epsilon r squared. So we ask, do we see on these trees at least epsilon r squared vertices? And it turns out that using Wilson's algorithm and running a second moment argument, we can indeed get that with a positive probability, even better than positive probability, 1 minus the polynomial in epsilon, we can get that the first epsilon to the 1/3 r trees, they contain epsilon r squared vertices, which is a nice thing. But then we want to say, okay, suppose the first batch of trees failed. We didn't find epsilon r squared vertices. What we expect maybe, at least intuitively, that if we look at the next batch of trees, at the next epsilon to the 1/3 r trees, the probability after the first failure to find many vertices only grows. But this is, okay, so we think this is true, but we couldn't prove this. We do have to use, the UST does have some negative correlations, but it's not as easy as I tried to explain. So our dream of just multiplying the probabilities as if these guys were independent, or multiplying these probabilities as if we had negative correlations, does not work, or at least we couldn't prove it. So we had to use something different. Let me maybe try to convince some of you that things can go wrong. So just for simplicity, I just talked about batches of trees. So now what I'll show is just what can go wrong for 2 trees. So I write T1 for the tree hanging on X, and I would write T2 for the tree hanging on the next vertex next to X. And what I want to convince you that it's possible that the tree hanging on X can be small, but that it also implies that the tree that is hanging on the next vertex will be small. And that's using this super nice drawing. So you see the tree hanging on X. It is small, but it's drawn this way. So you can imagine that it really blocks, we see the geometry of the graph. So it blocks the way for all other vertices to join T2. And then we get that not only that T1 is small, which is bad for us, it can also really destroy things for T2. And so if we look at the batches of trees, we might have that the first batch of trees is small, but also that it destroys the probability for the next batch of trees to be large. And indeed, we have some such bad realizations. But what's encouraging us is that at least on average, this is not the case. So what we would like to prove is that given that T1 is smaller than some k, the expected number of vertices we see on T2 grows. It can be only larger than what we expect to see without this conditioning. And I remind you that for the first batch of trees, we did a second moment argument. So what we want to do is to condition on the failure of the first trial, and then say, okay, we can still run the second moment argument afterwards. So this is taking care of the first moment. Okay, so here are T1 and T2 again. And I'll mention now the UST spatial Markov property, which says the following. We're going to condition now on some path phi to be in the UST. It will help us to prove this average thing that we wanted before. And what I want to tell you that if we know that this phi is in the UST, if we condition on this phi to be in the UST, then the rest of the UST is distributed as the UST of H mod phi. Now, what's H mod phi? You simply take all the vertices of this phi and you contract them into a single vertex. So you obtain a new graph and you sample UST on this new graph. And this is indeed how the rest of the UST looks like. And the second ingredient we'll need is a corollary of Feder and Mikhail from 1992, which says the following. So if you contracted this phi into a single vertex, so you have a new graph H mod phi, the UST on this graph is stochastically dominated by the UST of the original graph. Now, what does this stochastic domination implies? It implies that we can find a coupling in which we see the two graphs. So maybe I'll draw the two graphs in which we see that we have a coupling of the USTs on these two graphs, in which the UST on the upper graph, which is just H, will be larger than the UST of the lower graph, which is H mod phi. And then under this coupling that is guaranteed to exist, we get that T1 will always be larger on the upper graph. And so if we know that it is at least of size k in the lower graph, it's going to be at least of size k in the upper graph. So what we get is that given that phi is then the UST of H, the probability of T1 to be larger than k only decreases. Right? The probability of T1 to be large is bigger in the tree where we don't condition on phi to be in the UST. But since we have this for every phi that connects the vertex Z to T2, we can simply replace this conditioning on phi in USTH with Z in T2. And why is that? We can simply decompose this event according to what is the path phi that connects Z to T2. So eventually we get that given Z being in T2, the probability of T1 to be large only gets smaller compared to what would happen without conditioning. And so let's arrange the terms. So this is what we have from the previous discussion. We can take complements and get that given V in T2, the probability of T1 to be small only increases, meaning that these two guys are positively correlated. So using Bayes, we can just say that given that T1 is small, and we should think about it as the first trial failed, the first batch of trees is small, then the probability of V to be in T2 only grows. We then take a sum over all V's and get that indeed the expected size of T2 gets bigger once we condition on T1 to be small. So we have this on average. So we take K to be epsilon R squared. If the first trial of the first batch of trees indeed fails, so we know that the expected size of the next batch of trees can only grow. So we would like to run a second moment argument again. So it only remains to worry about the conditioned second moment. But this is, I guess, for another talk. So I will finish here. And thank you for listening. Thanks.
Thank you very much, Matan, for this very nice and interesting talk. So any questions to Matan? Maybe I'll ask a question. Besides the hypercube and the torus of dimension greater than 4, do you have another interesting example to share with us?
So every transitive expander will also have this 3 conditions: the transitivity, mixing, and escaping. We also suspect that that if you switch transitivity and you just have, say, a regularity at first, then the theorem will also hold. But the problem is that it relies on the theorem of Perez and Revel. This was our starting points. And in the paper of Perez and Revel, they showed this Gromov-Weak convergence under these assumptions. So we believe that if we can strengthen their result, and I guess that it's possible, then the result will also hold for regular graphs, not necessarily transitive, but also balanced graphs, for which the ratio between the maximum and the minimum degree is bounded. So we can also take smaller perturbations of the torus and of the hypercube, but this is not proven, not yet, at least.
I would like to add to Ron's question is that in the class of Cayley graphs or transitive graphs, this is almost dimension bigger than 4. It's almost everything. So every approximation of lamplighters, intermediate growth, expanders. So it's actually a giant class within the transitive graphs class.
Thank you very much.
Thank you.
And maybe a second question, what is known in 3 dimensions?
Right, so in 3 dimensions, yeah, I think we had Sarai, well, I don't know, a semester ago, which talked about the UST and Z3. So she talked about the UST in the infinite case and not about the torus. And I don't know if there is a direct proof, but the behavior is expected to be, so the way, for example, balls grow in the 3-dimensional torus should behave like it grows in the infinite volume UST. So a scaling limit of the UST in the 3-dimensional torus should have, for example, a different fractal dimension. But I don't know if there is really a result about the 3-dimensional torus UST scaling limits. Yes, I think that there isn't one, at least not an explicit one. Yes.
And also for the infinite one, there is no explicit scaling limit, just
yes.
Existence or not even existence, subsequential. Yes. I don't know.
No, Looper standard work is simpler. You do know that there is a limit, I think.
Okay.
It's not like, the other models where you only take sequential. In Looper standard work, there is a limit, so I assume, I don't remember exactly what Sarah and Omer and I forgot the other guy proved, but at least it's not like science fiction to show a limit.
There's a difference there between a torus and a box. Sorry, only in high dimensions it's a different behavior, right? In 2 and 3 dimensions, you don't expect a different behavior if you.
Well, limit is a problematic thing. You certainly don't expect a crude different behavior, but if you're talking about an actual limit, then yes, you do expect that since the works only do a small distance, since the works do get to the boundaries, the works that create the random trees, and you do expect a different limit. Maybe not. Okay, I don't have an opinion. Certainly not an interestingly different limit.
in your high dimensional setting, the limit would be different if you had different boundary conditions?
We're talking about finite graphs, so I don't really understand. So
if you took the box with I don't know, free boundary conditions,
it will be different.
Yeah. Yes.
Scale would certainly be different, because if you take wild boundary condition, then the typical distances are n square rather than n to d half.
Yes, exactly.
I don't know about the scaling limit, though. It might be the same scaling limit, even if the scaling is different.
Yeah. So in our case, really, when you take a path between two vertices in the d-dimensional torus, it really kind of goes over the torus many times. So the path really behaves like we were in the complete graph. But yes, if you wire things, so it becomes different. Yes.
Mm-hmm. Okay, if there are no further questions, let's thank Matan again.
Thank you.